Welcome to my projectbazaar.com. Let's discuss about the product. Our product is Synchronous Non-Volatile Logic Gate Design based on resistive switching memories. Emerging non-volatile memories, that is NVMs, based on resistive switching memories such as STT-MRAM, OXRRAM and CBRAM, etc. are under intense research and development investigation by both academics and industries. They provide high write speed, low power and good endurance beyond the maintenance stream, which allows them to be embedded directly with logic units for computing purpose. This integration could increase significantly the power die area efficiency and then overcome definitely the power speed bottlenecks of modern VLSI. This paper presents firstly a theoretical investigation of synchronous non-volatile logic gates based on resistive switching memories. Resistive switching non-volatile memories. Special design techniques and strategies are proposed to optimize the structure accordingly to different resistive characteristics of non-volatile memories. To validate this study, we simulated a non-volatile full adder with two types of non-volatile memories, that is STT-MRAM and OXRRAM. We are using CMOS 40 nanometer design kit and compact models, which includes related physics and experimental parameters. They show interesting power, speed and area gain compared with the synchronous CMOS full adder while keeping good reliability. Modern computing systems suffer from rising power dissipation, including both static and dynamic ports. The static power is driven by the high leakage currents, which increases exponentially with minimized of fabrication nodes. The dynamic power is included mainly by the data transfer between memory chip and logic units, which requires more power than the transmitter transistor switching, and then impose the speed bottleneck to adopt the current cooling systems. Lot of research from the device to the system level is under intense investigation to find a revolutionary solution to overcome definitely the bottlenecks. Integrating the resistive switching non-volatile memories such as pins transfer to magnetic RAM, oxide resistance RAM and conductive bridge RAM is widely considered as a promising approach thanks to their fast write-read speed, low switching and sensing power and good endurance. They are classified also memoristic devices. Firstly, their non-volatiles allows the system to be powered off completely in ideal state. This cuts down the significant static power, particularly for the normally off electronics such as mobile phones and notebooks. In 3D integration at the back-end CMOS process of these non-volatile memories shortens greatly the distance between memory chip and logic units from millimeters to micrometers. This lowers the dynamic power dedicated to data transfer and accelerates the access speed compared with conventional systems. This flow diagram states the proposed system design of our product. So our overall product is based on CMOS technology. So initially we are designing the MRAM, compatible MRAM, and in that MRAM we are implementing the design of STT, that is pins transfer clock, and non-volatile memory is considered within STT-MRAM. That means the overall design of STT-MRAM is a non-volatile memory. As an enhancement of this paper, we are implementing swapped CMOS design. So we are implementing swapped CMOS design inside the CMOS technology within STT-MRAM. So as a result of our enhancement method, we are reducing the power consumption.
This is the tool we are using for the simulation. This tool is called the Tanner tool. In Tanner tool, basically it has lot of sub devices. That means we are having SED, double edit, LED. Like this, we are having separated layout design for waveform designs and for circuit design. So similarly we are having separate lines for designing of separate parameters. So our CMOS design is performed in SED. So our performed design produces the output in WAD. The T-space, that means we can export the code of the designed circuit in T-space. So we can open the code in T-space and we can modify it as our requirement. So we are using, among this we are using SED for the circuit design, TED for the extra modifications, and WAD for the output design and analysis of the output waveforms. So this is the tool we are using for here. By clicking this we can start a new project. So to start every new project we have to open a new cell. So by clicking the cell we can design a new circuit design. So in the cell we can include lot of libraries which consist of transistors, CMOS transistors, resistors, capacitance, such as general devices. So after we designing we have to set the setup simulation. After that we have to save the file and we have to execute it. So if we executed the circuit in correct manner, we can get the output in WAD.
Thank you.